Assalamualaikum dan salam sejahtera. So we move to the next one. It's still in force convection, but external force convection. So we'll be looking at drag, heat transfer, and external flow, parallel flow over plate, flow across cylinder and spheres. So why we call external force is external force convection, because the flow, we only consider the flow externally from a solid object, on a solid object. So for external force convection, so two things we are going to look at: drag due to force due to drag. So for example, you have a car moving on this direction, and you have applied some pressure at behind, so you have a negative braking force. We call it a drag. So this will cause a drag on the car. So the drag is the force exerted by a flowing fluid on a body in the flow direction, and the drag can be classified into things. So first is pressure drag, and another one is a friction drag. So if you have a flat plate, if you have a liquid or gas flowing on a plate, so this is basically what experience or what the thing that experience on the plate is a friction drag only. So there is no uh, pressure drag on the surface. So basically friction drag due to viscosity. So if you have a plate that has experiencing flow in 90 degrees, that looks like this. So there is only drag force on the flat plate due to pressure drag. So if the flow hits the surface in the perpendicular manner, so it will be a pressure drag. If we hit the plate in the same direction or same length of the plate, so only friction drag occurs on the surface. There's two different things between the friction drag and the pressure drag. So drag due to the wall shear stress, which we call a skin friction drag. So drag due directly to pressure, we call it a pressure drag. This is basically due to viscosity friction. This is due to pressure. So drag force combination of wall shear stress and pressure force. We can have both things, so friction and pressure drag in the one phenomena. Friction drag is strong function of viscosity. So this is a basic of fluid mechanics. So higher viscosity, you will have a higher friction drag. So for external flow on a cylinder, so let's say you have a cylinder with some length. So the length is in the direction of in the screen. Okay, so we cannot see the length because it's the z-axis is into the screen. So we assume it to be a two-dimensional. So let's say we have a flow. So what happened in this point, and we experiencing a strong pressure drag, and we also have uh, friction drag, okay, due to viscosity or in this region. Okay, so at some point it will the flow will attach on the surface and then reattach and attach back. Okay, this is the physics of the flow across cylinder. So the reattachment we call a wake. So pressure is really small behind of this. So that's why if you don't hold the cylinder, so the cylinder will go back because of the high pressure over in this point. So what is the relationship? What is the interplay between drag and heat transfer? So drag and heat transfer basically interrelated. So it depends on the geometry, type of fluid, and its flow regime. So coming back to the Nusselt number. So we know that the Nusselt number is a function of the Reynolds number and Prandtl number. So why NUX? Because this depends on, let's say you have the plate. So Nusselt number on each length of the plate depend on your Reynolds number on a certain length. So Prandtl number remain constant. So Prandtl number, you need to have the average temperature and you have the value. But Reynolds number depend on the length of the plate, and then you will have a Nusselt number average. The Nusselt number depend on the length. But sometimes your plate is just let's say very short, so you don't want to consider the local nasi number. So basically nasi number over here is different, nasi over here is different due to different flow regime. This is lamina and that is turbulent. So you can also take into consideration to take just average nasi number by calculating the average knot number over the length and the product number. So in this case, we have just NU without X because we are taking the average. But most of the time, we are taking average. So based on this, we have the equation for Nusselt number. Remember that Nusselt number is equal to HL over K because we want to determine the H or heat transfer coefficient. We equate this equation to the HL over K. So this is the main equation. Okay, but the equation will change depend on the flow physics, depend on the geometry of the solid body. All right. So previously we have looked into the lookup table in which you can point out the value of density, point out the value of thermal conductivity of air or liquid, and you can point out the value of Prandtl number. So that all the values depend on the temperature. So how to choose which temperature you are going to use in order to find all the parameters. So basically, the temperature that you're going to use for determining working fluid parameters is basically a film temperature. This is the average temperature of the surface. Okay, this, let's say you have a hot surface, you have a colder environment. So let's say this is 50 degree and your environment is 25. So 50 plus 25 divided by 2. The result of that is the temperature that you are going to use for finding all the heat capacity. The thermal conductivity, the Prandtl number depend on the average temperature. Okay, so you don't use the surface temperature, you don't use the ambient temperature, you use the average temperature between these two for finding all the parameters in the table. Okay, so calculating the Knox number. Okay, let's say you want to calculate the Nusselt number based on its length. Okay, you need to consider the value of speed at certain point. So this is why this Vx and Dx Reynolds number at point X. Okay, otherwise if you given the average velocity, you can calculate the Reynolds average rather than calculating the Reynolds at certain point. So the good thing calculating Reynolds because you will know that whether your flow is laminar or turbulent because the Nusselt number correlation. So Nusselt correlation is depends on the value of the Reynolds number as well. If you're working in this laminar area, so your equation for Nusselt number is different. So if you're working in turbulent area, your Nusselt number will be different. That's why you have a different heat transfer coefficient for laminar and different heat transfer coefficient for turbulent. So this is the correlation. You don't have to memorize this because this is given in your textbook. You can use it, but you need to check. Let's say you're calculating based on this one. This is your problem, and you calculate that the Reynolds number for this problem, and you get the value Reynolds number less than 5 to the power of 5. And then from the temperature, surface temperature and ambient temperature, you calculate that divide by 2. You're taking the average temperature, and you find the Prandtl number, and the Prandtl number is larger than 0.6. Then you can use this correlation, okay, to find the Nusselt number. So you calculated Reynolds number, you can put over here. You calculated Prandtl number, you can put over there. And then you know the thermal conductivity of your working fluid based on the film temperature or average temperature and the length of your problem. So this is known. This side is known from the table, and this is from the geometry. And then you can find the heat transfer coefficient or the H. So let's say, for example, your Reynolds number is 8 to the power of 5. Sorry, less than 5 to the power of 5. Let's say 4 to the power of 5. 4.5 to the power of 5, which is less than 5, and your Prandtl number is 1. So you can use this equation and you can plug in 4.5 to the power of 5 and Prandtl number to 1. You know what is your thermal conductivity of your working fluid, the length, and then you calculate the H. So if your problem is fall under turbulent, okay, you need to use this equation for flat plate. Okay, so this is different. So Nusselt number for laminar is different. Nusselt number for turbulent is different. So what? So these two equation, so will give you something different on the heat transfer coefficient and also the skin friction. So looking over here, if your flow is in laminar, your heat transfer coefficient will be low. If your fluid, if your fluid is in turbulent, your heat transfer coefficient will be high. So that's why you want to cool faster. You need to ensure you're working in turbulent, so you can have high heat transfer coefficient. And that's why the equation are different for laminar and for turbulent. So this is for a fixed temperature. Let's say you have a uniform heat flux over here, okay, and then you calculate your heat transfer coefficient based on this equation, okay, Nusselt number correlation, and then you know the H, okay, and then you can calculate whether the Q dot heat transfer or the surface temperature on the surface of the plate. So if you have a flow over cylinder in Zephyr, so this is a bit a recap from the first earlier part of it. So for tubes and balls, cylinder in Zephyr, the Reynolds critical is 2 to the power of 5. So larger than this or equal to this is going to be turbulent. So the drag force is primarily due to friction drag at low Reynolds number. If you are working with low Reynolds number, friction drag, and high Reynolds number is due to pressure drag. So high pressure in the front, okay, basically low pressure and plus low pressure at the back causes the cylinder to be moving backward if you don't hold it. So if you are working with Reynolds number less than 10, mainly friction drag, mainly due to viscosity. If a high Reynolds number is mainly on pressure drag, which is you have high pressure on this front of the cylinder. Alright, so for cylinder and sphere, the correlation for Nusselt number is this one. But you need to check. You need to check your Reynolds number multiply your Prandtl number must be larger than 0.2, 0.2. And then you can use this equation. It seems that equation a bit tedious, mathematically tedious, but it's a very simple, I think it's a very simple correlation. You don't have to do any mathematical operation like integration or differentiation. You need to include the boundary condition. No, you don't have to. You just use this equation. Okay, what is your Reynolds number? One first thing you need to check your Reynolds number, multiplication of Reynolds number and Prandtl number must be larger than 0.2. That's the condition. When this is for the correlation for flow over cylinder. So this is correlation for flow on a flat plate for laminar and turbulent. So this is different. That's why we have a different correlation based on your physics, based on the geometry, and based on your certain condition laminar or turbulent. So in this case, you need to calculate your Reynolds number and what is the Prandtl number, which is you evaluate the Prandtl number based on the average temperature on the cylinder and the ambient condition, the average the temperature, and then multiply the number and Prandtl number. If your result is more larger than 0.2, you can use this equation, okay, because we want to determine the heat transfer coefficient, the H. If you can calculate the number, you can find the Prandtl number for sure. You're going to find the thermal conductivity of the working fluid based on this film temperature or average temperature. And then you need to rearrange this equation and find the heat transfer coefficient. Alright, this is for over cylinder. You can also use this correlation. You can also use this correlation for a circle because it seems like a cylinder. Okay, but you need to check the Reynolds number. If your Reynolds number is between this region, you need to use this equation, this formula, this correlation, and equate this to Nusselt number is HL over K. You find the H. Let's say you are working with 40,000, the number of 40,000. So then you choose this equation. This is the correlation to find your Nusselt number and correspondingly find the heat transfer coefficient. So in general, this is the equation. The C value is determined by experiment. So we don't do the experiment. This is basically they did the experiment before and then make a correlation. So if let's say your system, your solid is square, your Reynolds number between this region, and you use this Nusselt number correlation. So this will be given as well in the final exam, in a table. So you need to make sure you are working with, you are choosing the correlation based on your physics, based on your geometry of your problem. Okay, this is some example. So let's say you have a rod 10 centimeter, 10 centimeter diameter and 1 meter length. Okay, you want to calculate the heat transfer rate from the pipe, from the cylinder to the ambient condition, because the surface of the surface of the cylinder is, the our rod is 110, while the ambient temperature is 10 degrees C. So before start to do it, this problem, because start approaching this problem, you need to find the surface thin film surface temperature, thin film temperature. Sorry. So basically, T surface plus T ambient divided by 2. Basically, 110 plus 10 degrees C divided by 2, so 60 degrees C. So 60 degrees Celsius is the temperature you want to look at in the table A15, which is the you need to find the parameters of the air based on this temperature. So from that, you can find your thermal conductivity is this value, your Prandtl number, this value, and kinematic viscosity in this. So next, you calculate the Reynolds number. So you have speed, 8 meters per second. You have the diameter of the diameter of the rod is 0.1 meter. You need to change to meter from a centimeter. And your kinematic viscosity is this value. So from here, you figure out your Reynolds number is 4.2 to the power of 4. So based on this, you can use this equation. Okay, firstly, because it's a cylinder, and if you multiply your Reynolds number with the Prandtl number, okay, basically you will get a result larger than 0.2. So it allows you to use this equation to find the heat transfer coefficient. Okay, let's check. So this is the result. This is the correlation. Okay, this is the correlation, and then from the correlation, you will find the Nusselt number is 124. So basically, Nusselt number is equal to L. So in this case, your L is going to be D, because this is a cylinder, divided by K. So you know D, you know K, and the next step is to find the H. So this is the Nusselt number you have calculated. The thermal quality of the fluid, the air, sorry, 0.02808, and the diameter is 0.1. And now you can find the heat transfer coefficient is 34.8 watt per meter squared Kelvin. Okay, so next step is to find the heat transfer rate from the rod to the ambient. So you need to use this equation, Newton's law of cooling, HA delta T, which is T surface minus T ambient, because surface is more hotter than ambient. So you need to subtract T surface to T ambient. So the heat transfer coefficient is obtained from this correlation, and you have calculated by using this equation. Okay, 34.8. Your surface area is basically pi d over L. So all the external surface area. Okay, and then they are different in temperature. So you get your answer is 1093 watts. Okay, so this is one correlation. You can also use correlation of the circle. Okay, because the flow is from here approaching from left hand side, and it flow over here. But you need to check, since your Reynolds number fall under this region, okay, between this region. So you can use this value, this correlation, and you will get more or less similar to the Nusselt number as 1 to 4. So if you use this equation, you will get Nusselt number is 1 to 8, slightly different, but not that much. So you can use this one, or you can use in the table. But I suggest you use this one because it's more general. It fits the criteria easily, because you need to multiply Reynolds number with Prandtl number, and then must be larger than 2, and then you can use the function. So this is a second example. So we have long aluminum rod, 1 meter length, diameter 3 millimeters, is cooled by cross air flowing. Okay, the surface of the temperature of aluminum is 280, and ambient is 20. So basically you want to cool down the rod. So calculate the rate of heat transfer from aluminium to surrounding. So first thing first, we need to determine the thin film temperature. Basically the average of the surface with the ambient. So 280 plus 20 divided by 2, 150 degrees C. So the 150 degrees C is the temperature you want to look at to find all the parameters. You want to find the K, V, and the kinematic viscosity and the Prandtl number. So this is the table. Look at 150 properties of air, 150, and you can use all the value that you can choose the value that you want. So density, you might want to consider specific heat. Most of the important thing is thermal conductivity and the Prandtl number. Okay, next you for the and you finish obtaining all the air parameters based on this temperature. Next, you calculate the Reynolds number because you want to choose which equation, which correlation you need to use. From here, your Reynolds number is 6 to 9.4, and then you multiply Reynolds number with your Prandtl number, so you get 400 something, 442 to be exact. And this pass the condition of Reynolds multiplied by Prandtl number, which is larger than 0.2. So 442 is larger than 0.2. So you can use this correlation. Okay, the next step is just plug in your Reynolds number, plug in your Prandtl number, and then you get your Nusselt number. So your Nusselt number is equal to HD over K. Next, you need to find your heat transfer coefficient. So from here, heat transfer coefficient of 145.2. Next, you want to calculate the heat transfer rate, which is from Newton's law of cooling, the heat transfer coefficient multiplied by the surface area and delta T. So in this case, T surface minus T ambient, because T surface is much more hotter than the ambient. So heat transfer that you get is 145. Area, you calculate external area pi d over L, the external surface, the whole external surface of the this rod, aluminum rod, and then you get the answer 356 watts. Okay, that's all for external heat transfer. Thank you.